be able to do all the homework from 13. And so if some of you already asked if it was due today, and I was thinking no, because there's more I want to do, but turn in chapter 13, hopefully sometime this week. If not on Wednesday, maybe in the MC. I'll still take it on the day of the final, but don't tell anyone. But really want to get that in as soon as you can. It's for two reasons. One is that I can get it graded so that I can have that all stuff done before I get your finals. And two, I think it's good to just do the homework, get it out of the way so that that's not in your way as you study for your finals, both this class and other classes. So that's the idea. And I say all that because then 14, although we are going to be talking about 14 and we are going to be saying that there's one problem on the final from 14, you don't need to turn in the homework. And so that's just a long way of saying there's a whole list of problems here. Most of them you will be able to do. We will have enough time to talk about most of them, but maybe not quite all of them. But the bottom line is you are responsible for what I talk about in class, as far as we get in class. And so if that means for you to do all of the homework, then do it. In fact, I would even encourage it. But obviously you need to study the material. That means, of course, read it as well as hear the lecture on it and watch me work on it. But that's the idea. And in fact, I'm just going to work through the rest of chapter 13 now and get started in 14, as I said, so that hopefully we will get to Archimedes Principle and just kind of skip doing any examples from 13 until we get to Wednesday. And my goal, hopefully then on Wednesday, is to finish what I don't talk about today from 14 and then just do examples for the rest of the time that we have. Some from chapter 13 and some for chapter 14. And that will wrap up the semester. So again, here's the big picture, is finishing up through chapter 14. And that means lecture today and Wednesday with examples on Wednesday, going over the test in the lab today, as well as doing a short Archimedes lab, and then finally a final exam then in 9 days. Wow. So in 9 days and 2 hours, you'll be done with this class. You probably won't sleep for 9 days and 2 hours, but actually, no, since Wednesday might be your last one. It was getting closer to the end, so maybe you get some sleep after the final exam. But don't turn in 14. That was a long way of saying you're responsible for what we're talking about in 14. There is going to be a problem on the final. But 14, I'm not going to grade. I'm not going to look at it. So use your best judgment call on what works best for you to learn the material. Don't spend the hours doing all the homework if that's not best for you. For others, it is, right? So, but definitely, I would always say for everybody should practice some problems, and you know. That's always, I think, an obvious one. Practice some problems, as well as I will show you some problems on Wednesday, depending on how time goes. All right, so that's, like I said, today's lecture, and then Wednesday, the last lecture, and then final exam the Wednesday after that. That being said, then, let's go back to where we left off, because we left off on the last and the hardest part of chapter 13, and that was the gravitational potential energy. I'll begin by saying chapter 13 introduces you to Newton's universal law of gravity. And what Newton said is that if you had two objects, one being of mass m1 and the other being of mass m2, and they are gravitationally attracted to them, or I should say just because they have mass, they are gravitationally attracted, and that this spacing between them is this r, then this would be the numerical way of calculating the force of gravity between them. And so I spent the last lecture saying that this is the only new piece of information that you're given. And then we went back and we said, let's apply this to what we have learned before. And without repeating everything we did, one thing that we did is we said if you had something going in an orbit, let's say you take the Earth going around the sun, then we know that the force is the force from the sun and the force from the Earth divided by the distance squared. We also know, as we went back to chapter 6, that the object going around times the velocity of the object going around times the radius going around is what we call the centripetal or the radial force on it. We canceled those off, we canceled these off, and we got velocity equals the square root of g, mass of the sun, over the radius. And so this was the equation that we saw for the velocity. And so we did a bunch of calculations. I think we talked about the International Space Station, and we figured out how high it was and how fast it was going. We then said the velocity would be the the distance, which is the circumference, 2 pi r divided by the time it takes to go around. And we could then figure out how long it took to go around. And I think I remember getting 92 minutes, if I remember, for the International Space Station. And we did a bunch of other things, but here was the big one. The big one, where we left off and where I want to finish here today, was with gravitational potential energy. Because this one, where the equation is mgy, was derived by saying that this is the integral, negative the integral, of the force of gravity as you lift it up. And of course, that gave us this equation. However, I'll cross it out, because one of the points I was trying to make here is that the force of gravity now is no longer really a constant. It does change with position. And we pointed out and did some numbers that if the position doesn't change by that much, what do I do with my calculator? Good. If the position didn't change by that much, in other words, if you just stayed within the Earth's atmosphere, so if you're flying in an airplane or climbing on the mountains, you're really not that high. And this number doesn't change by much. It's why you don't notice that change in weight when you go up in the mountains or up in an airplane. And so this equation was certainly valid for what we had been using. And I would encourage you to continue to do that. And in fact, when we take the final, as well as go over the test today, one of the things that makes the test a challenge and the final a challenge is, now that we've done so much material, you've got to start off and say, what type of problem is this? Is this a conservation of linear momentum problem? Is this a conservation of energy problem? Is this a conservation of angular momentum problem? And you, of course, notice that on the test, as well as now that you've been working along, that those are the parts you have to stop and ask, how do I handle this problem? What is the basic physics that was going on? And we had the first test, it was much simpler because we only had one main topic. But then, now that we're deep into the semester, and it just gets more so as you get more and more education and you can do more and more complicated problems, you begin to look and say, oh, what type is this? Which, now that I'm standing here, I'll say, if you guys want to pick up some more pieces of homework, I'll send those around. But in this case, then, I would say that if you are having something that is going higher than the Earth's atmosphere, you would not want to calculate it with a constant gravitational force of mg, as where this was derived for. And so if we take, like, say, a baseball and give it so much speed that it doesn't just go up a few feet or even a few hundred or 1,000 feet, but maybe 1,000 miles, now we're talking something totally different. We're talking where the force of gravity does change. And we've got a whole new set of problems, but the concept is still the same. And so we left off by saying now that the force of gravity then would be negative the integral of g m1 m2 r squared dr, as you had something like, say, the Earth, then that has an object that goes really high before stopping and coming back down. And so when we did this, we came up with a negative g m1 m2 over r, and that's where I want to pick up. So this is where we left off, and this is the one that I said I think is the hardest equation to, I think, really comprehend here, because it looks so radically different than what we had done before. What we had done before, of course, was to treat the force of gravity as a constant. And when you put in a force of gravity as just simply mg, the integral is much simpler than something like this. More than that, when you put in a force of mg, all you're saying is which direction is positive and which direction is negative. You're not saying where 0 is. And so I'll say it again, and it's worth repeating. Back in chapter 8, when we used this formula, mgy, we kept saying that if you're going to use that formula, you must call up positive and down negative. But you can choose the 0 anywhere you want, because it hadn't been chosen in that derivation. And we did that many times. In fact, that was just the opposite of when we did the gravitational potential energy from a spring, which, since we're getting close to the final, it may not hurt to compare those and just kind of review. This is the gravitational potential energy from a spring. And if you remember doing that one, that came from the integral, the negative of the force from a spring. And the force from the spring was the negative kx. That was the Hooke's law. And again, as we studied Hooke's law, please remember that Hooke's law meant that 0x was at the natural length of the spring. So if we were going to use, and we did use Hooke's law, we must use x equals to 0 as the natural length of the spring. We're locked into that once we use that equation. Now, that being said, now that we've re-derived the equation for potential energy here, let's see what we have done. Because this equation, right back here, defines the distance between them. And so r equals to be 0, we don't get a pick anymore. R must be measured from center of mass to center of mass. It's chosen for us in that equation. So just like in Hooke's law, but unlike we did with the other gravitational potential energy, we do not have the freedom when we use that equation to pick 0, say, on the surface of the Earth. We can't do that anymore. And so we are locked into that definition of what R means. And a consequence of that, if you look closely at that, then you will see that you have potential energies that are always negative numbers. If I were to say, look at the Earth here, then I would say that right here, if I was standing here, I would have a potential energy due to gravity that is negative a big number. And I forget what we got on Wednesday, but we actually got something in the billions of joules, negative of billions of joules. And so that was my point. It would be a negative. And if you went up, the number, the potential energy, would get smaller. But remember, when you're dealing with negative numbers, that means you're just getting less negative. And so it's still negative, and it's not until you get to, and I'll just say R approaches infinity, is when the potential energy then approaches 0. And so what I was trying to say is it may seem a little bit odd at first, and that's where I want to go back to and finish up the chapter here, but 0 energy is a lot of energy. 0 energy is the amount of energy you or I or a rocket must have in order to be infinite distance from the Earth. And so to what we were going to say now, escape from the Earth. we have to have so much energy that our total energy is equal to 0. And so again, it sounds funny, but keep in mind, as you and I stand on the surface of the Earth, we have a negative billions of joules of energy. And so to get all the way up to 0 energy means you got to give yourself a lot of energy. Watch this. Let's put this into an example. Because, again, want to emphasize, not doing anything different than the other chapters, other than I'm using this new equation called Newton's universal law of gravity. But if I were to actually work on a problem like this, I take a baseball, let's say it has a mass of m, and let's say that I throw the baseball at some incredibly large speed. How about give an initial speed of 3,000 meters per second? How high would it go? And I hope the first thing, if you saw this problem, you would go, okay, that is going really fast. There is a really good chance that that is going so fast that it'll have to go higher than the Earth's atmosphere. And because of that, I do not want to use a potential energy of mgy. I would want to use a potential energy that is more appropriate for one that actually varies significant distance. So with that in mind, I would still attack it the same way. I would say, okay, this is a conservation of energy problem. When we talked about, you take a pen and you throw it at 18 meters per second and you ask how high it goes, what we would do is we would say the initial, well, let me do kinetic. The initial kinetic and the initial potential would then equal the final kinetic and the final potential. That's the normal process that you would do, right? And again, that's the kind of lesson we learned back in Chapter 8. And let me just do the same thing. In fact, I probably hate to say too much along these lines because we're going to go over the test in a couple of hours when we get into lab, but isn't that how you would calculate a rod that was hit by a bird and now is falling? Right? You would say, what does energy it have at the top? What energy does it have at the bottom? And so 4b is exactly that same problem. It is a conservation of energy problem. Question? Yeah.
If you integrate a negative number, like if you integrate that negative number with respect to r, would it become a positive number? Because like the integral of 1 over r squared is negative.
Fair enough. Let me do a little more detail. The potential energy is negative of the work. The work is force dotted with distance. And what I carelessly did too quickly was to say that, okay, this is a negative, and then the force of gravity is down, so there's the negative, and the magnitude is this. And that's really what I should have done, a vector. So, yeah, so that really needs a double negative. Then, and I think you see the last step, once those two negatives cancel off, and then I integrate that, G m1, m2, I get a negative there again. So yeah, there's a lot of negatives going on, and I carelessly left off that this is a dot product and direction matters, and that's why we need to call moving outward positive and moving inward negative. Yeah. All right, so back to this problem. Yeah?
Kind of I mean, it's on topic kind of, but I was watching it at 60 Minutes, and us Americans launched a satellite some 17,000, 18,000 miles up into, just up.
Yeah.
And some other country tried to top us, tried to go a little bit past, and the satellite then just exploded and left a lot of debris and everything, which is really bad, obviously. But what was the explosion totally? I mean, don't we reach like zero gravity, zero energy, as you said up there? Why would there be just, is there so much lack of?
Are you asking why it exploded?
Yeah.
I mean, the rocket probably exploded.
Okay, I don't know what I was asking, but
yeah. But unfortunately, up here it's turning into a big debris field because as rockets go up and you try to put them in orbit, sometimes things can go wrong and explode, or maybe not even just wrong, but they carry along fuel tanks that you use to propel, and then you kind of just separate those out. But they're in orbit, so they're going to just keep going around and around and around and around, right? And so we're back to, I guess I erased it now, but the same thing we did on Wednesday, that this, there's the force of gravity, if you will, is not making them go faster. The force of gravity is turning them. So there is a force of gravity up there. But it doesn't make them fall to the earth, they just makes them turn, and so they just go around and go around. So if you want to put something up here, then it's in danger of colliding with that other debris that's up there. Yeah. So it's one of the reasons why, in fact, when we left class on Wednesday, I was kind of curious because and you looked it up online. But I was saying, is the International Space Station at 250 or 300 miles up? And you looked it up, and it was 250 miles or 249 or something like that. And then I did the Hubble satellite after class, the Hubble telescope. That's at 300 miles. So those were the two I was kind of mixing. But one of the arguments I understand of putting the Hubble satellite or telescope so much higher was to get it out of this debris field. Most of this debris sits down low. In fact, the lower the better, because these are the ones that as they go around, there will be a small amount of air resistance that eventually it will slow it down, and eventually it will hit the atmosphere, and then they eventually burn up. In fact, that's going back to the Hubble one. When I looked it up, it said that the Hubble should slow down and crash back to the Earth in I want to say 2030. So it's still going to go around for quite a while, but it's going to crash and burn, and yeah. In fact, what I learned and didn't know also is that the last time they made a mission to it before they retired the space shuttles, knowing it was pretty much the last one, they hooked some kind of, I'll call it a connecting pod for lack of a better word, onto it so that they anticipate that they're going to have to send up some kind of rocket that will attach and lock on so that they can kind of control where it's going to crash. Don't just kind of let it crash. Oh, yeah, it might hit Santa Barbara. Yeah, Santa Barbara's a small place. What's the chances it's going to hit Santa Barbara here? But they do want to make sure when it gets close, they can then figure out when to ignite the
track that Russian ship that just went up and went out of control.
Oh, did a Russian one go out of control?
Yeah, there was a ship went up to the space station that something went wrong with it. They said they have no way of navigating it or knowing where it's going to
come back. Yeah, bummer. Yeah, and there's been a number of cases where they haven't been able to control it real well. Again, fortunately, most of these are small enough that they burn up. But again, back to the Hubble one, because they say that mirror is so thick and heavy that they expect it to last all the way and still be a solid piece when it hits ground. So we want to make sure it hits water, some ocean somewhere, not. You, like me, may be old enough to remember the old Skylab coming down in the 70s. Yeah. So again, that one they tried to control it, and they didn't it hit Australia, I want to say. Yeah, I think pieces fell over Australia, so they didn't. That was our first space station. So didn't quite control it enough. They just didn't have enough fuel and enough to control. They were trying to get it to. I can't remember if they were trying to ditch it before and get it to land in the Indian Ocean or after Australia and in the Pacific Ocean, and they kind of hit the middle ground, landed in pieces of Australia. Anyways, I digress here. So back to this problem. So this problem is, I hope you recognize right away that it would be a conservation of energy problem. And it's a good problem in the sense that it's the same physics we've been doing, but I got to use the new set of ideas, and in this case the new formula, because this one is going to go really, really high here. And so if I stand back and I do my calculation, I guess I would say 1/2 m, and then I would put 3,000 meters squared. So there is the kinetic energy that this ball would have, say, on the surface of the Earth. I'll call this the initial. This is the speed I give it. And then when I go ahead and I say, what is the initial potential energy? That's where the negative 6.67 times 10 to the negative 11. Then the mass of the baseball. Then the mass of the Earth. Then the R. And this is, again, a good example to say that not only do I have to use this equation because it's going so fast it'll probably go out of the Earth's atmosphere, but I need to remember how this equation is used, and it is used in the sense that the R here is measured from the center of the Earth. So this would be the radius of the Earth, that 6.37 million meters. And so there would be the first part of my calculation. And in fact, maybe it's even worth doing these separately. I said baseball. I'm not sure what the mass of a baseball is.
Are we going to have to remember the masses and radiuses of the sun?
Oh, no. Yeah, and so when we get to the test or the final there, I will give you the radius of the Earth or the mass of the Earth. Sure, certainly. Yeah. I'm not sure if I will bother to copy this whole table that I've been using. Or since it's just going to be one problem, maybe I'll just copy part of the table to give you the parts that you need. But I will definitely give you things like mass of Jupiter or Sun or Earth, whatever it is you need. Yeah. Don't expect you to memorize it. The only one I do expect is the universal constant. Right, because it's universal. Right, it's used in every problem. Right. I'm going to guess that a baseball is 150 grams. I'm not sure exactly what it is, but maybe it's worth seeing some numbers here, because over here, if I go 1/2 times 0.15 times 3,000 squared, this comes out to be a positive 675,000 joules. This one here, again, it is going to come out to be negative, as to be expected. Our potential energy will always be negative based upon this idea. And so if I put this number in, 6.67 times 10 to the negative 11 times 0.15 times 5.98 times 10 to the 24 times 6.37 times 10 to the 6th. This comes out to be a negative 939. Maybe I'll just do three significant figures. 1, 2, 3, 4, 5, 6. Joules. Okay? And so again, notice it is negative. Notice it's a very large negative. And again, notice I've measured from the center of the Earth. So this is negative 9 million. And so if I take this 675,000 and add it to that negative number, notice then I come out with a negative, and this I guess would be 8,717,000 joules. And so I would have to say that the total energy is negative. Now, before we finish the problem, let's talk about that. Total is negative. Now, the reason I keep emphasizing that is, would this object that is going so fast actually ever stop? In other words, what is thrown up, does it always come back down? And if you remember on Wednesday, I promised you that I would show you 0 is actually an interesting number to work with this way. And so although at first this formula looks really annoying, it's actually very helpful. Because here's what it's saying. It is basically saying if you took an object, so say here's the Earth, and you got further and further away from it. I know you can't literally get infinitely away, but let's say you get infinitely away. How much potential energy would it have? 0. And if it is moving at all, then it would have a positive energy total, right? And since energy is conserved, way back here when it was on the surface of the Earth, even though it had a negative potential energy, would it have a large speed? That the total speed would then give it an energy greater than 0? Right. Let me say it again. If you had something that never came back to the Earth, you threw it so fast that it would never return to the Earth, that means that some many eons later, it would be an infinite distance away, so 0 potential energy, and either still moving forward, or you might say barely moving, or you might even say stopped. But if you say stopped, then what's the total energy over here? 0. And since it got all of its energy back here, now granted, when it was back on the Earth, it had a lot of negative potential energy, but it also had a huge amount of kinetic energy. And so here's my point. My point is that in order for something to go so fast that it never returns to the Earth, we're saying that the total energy would have to be what? 0, right? You have to have so much energy equal to 0, then it would never come back. Now, notice mine is not quite that big. I do not have 0 energy. Don't I have something less than 0 energy? So what does that say about my particular problem? Yeah, it's going to come back. We call this then trapped on the Earth. It's like throwing up this pen. It's going to come back. I throw it up. Unless I throw it fast enough, it's going to come back. How fast is fast enough? Well, let's answer that next after we finish this problem. But that's an interesting question. I can tell you right now, it's got to be more than 3,000 meters a second. Because this math is telling me that I've got this much kinetic, but this much negative potential. When I add it together, it's negative. It's still very negative. This thing's not even going to come close to escaping the Earth. It is going to slow down and come back to the Earth. Now, it'll probably go much higher than the Earth's atmosphere, but it's going to return. Yeah. So I'm going to call that the escape velocity in a second. How fast do I have to throw something that it would escape from the Earth? Okay? But what I wanted you to see is why using this formula then, although it's a little annoying at first, it's actually kind of neat. It tells us that anything with energy greater than 0, and notice I'm talking about total energy. So something that has a potential plus its kinetic, if it is greater than 0, then that means as it leaves the Earth, although it's slowing down, it will never slow down to a stop. Because in order to stop, it would have to have negative energy. It would have 0 kinetic, and it would still have some potential. And all the potential is always negative. So anything that has 0 total energy or greater will never come to a stop. And that's going to be our key for figuring out what we'll call the escape velocity. How fast do you have to throw it? And this is much lower than the escape velocity, obviously. Fair enough? Well, let me keep going, because this first part of my question was just how high is it going to go? And so I've calculated the initial energy. The other side of the equation, I guess I would write this way. I would write it as G m1 m2 over r final. And so this would become a negative 6.67 times 10 to the negative 11. This would then be the mass of that baseball again. This would then be the mass of the Earth. And now I can go through some arithmetic here and get R final. How much does it need to go? And so taking this 6.67 times 10 to the negative 11, multiplying it by 0.15, multiplying it by 5.98 times 10 to the 24, and then dividing it by, and the two negatives cancel off, that's good, this 8,717,000, I get an R of 686, and I'll just do 3 significant figures. 1, 2, 3, 4, 5, 6. So that is saying R is 6.8 million meters. Okay. Now, fair enough, but the first 6.37 million meters is the radius of the Earth. So if I'm drawing a picture here, and I know this is then R final, and then this is 6.37 million, then if the question is saying, you know, how high does it go before it comes to a stop, and maybe I should emphasize, notice I said come to a stop, so this side was a final kinetic energy of 0. Okay, I can then be saying here, let's call this then H. I have H plus 6.37 million meters, and so here is my H. And so subtracting off 6.37 million meters, I get this 493, actually I'll round it to 94 meters. Actually, I thought it would go higher than that. But there would be the height. If, like I said, if it was shot up at that speed. And of course, now I think you could do this for any speed, right? You could say 3,000, 4,000, 5,000. I'll take that next step. My question number 2 then. How fast would an object have to be traveling in order to never come back? What we'll call the escape speed. Well, that's what I was trying to argue here, that although this negative for the potential energy looks a little annoying at first, it's actually quite nice, because here's what you're saying. You're saying if you take the initial kinetic plus the initial potential, which is your total energy, if that is greater than 0, the object will never stop. Anything that is less than 0 means that at some point it has 0 kinetic energy, it stops, and that is its potential energy at that point, and then begins to fall back towards the Earth. So let's write it this way. When does this energy add up to be 0? And obviously, quite clearly, 3,000 meters per second is not enough. Apparently not even close to being enough. But I can write it this way. Here would be the kinetic energy that the object might have on the surface. Here then would be the potential energy that the object would have on the surface. And I want that to be greater than or equal to 0. And then here's where the math is kind of nice to have a 0 in the equation. You can just move it to the other side and you get 1/2 times the mass times the initial speed squared, g mass 1 mass 2 over the radius. I guess we should point out here that the moving object, I'm going to label as number 2. So number 2 here would cancel with each of those. And so the initial speed, and I should say greater than, 2 times the mass of the planet divided by the radius of the planet square root, then if that is true, then it will escape. Your author writes this as VE I don't know. I think he puts 2 symbols in there. And I didn't write it in my notes, but I thought he didn't want to use the E because we used the E for the exhaust speed for that rocket problem back in chapter 9, if you remember that far back. So I was pretty sure he did something more, and now I can't remember what he did, but I'm going to look it up here. He did something like a prime or V naught. I don't. Kepler's first law, gravity. All right. Satellite motion. Oh, he just go. Okay, there it is. He just goes ESC. That's what he does. ESC. Okay. So he just says escape speed. All right. So escape speed is that number. And I'm kind of curious to what this is on the Earth. So how high would or how fast would I have to throw something? So let's look at the escape speed from Earth. And so it would be 2 times 6.67 times 10 to the negative 11 times the mass, and let's get it straight, which one was this? This would be the mass of the planet you're trying to escape. So this is the 5.98 times 10 to the 24th. And then on the radius, or at least from the surface of the Earth, 6 million meters, gives me, and hopefully I get the classical 11,200 meters per second. Let's see. 2 times 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24th, all that divided by 6.37 times 10 to the 6th, and taking the square root of all of that, is my 11,200 meters per second. So if I go that fast, I will never stop and come back. So obviously the 3,000 I picked was way low, and it's gonna come back. Yeah. As opposed to?
Would it be different if, like, you went, like, you started orbiting the Earth and then...
Well, I guess I'm trying to figure out what you're after, because if I were to go straight up or straight out, I would argue it's the same thing essentially. Right? I got to escape from the Earth, left, right, up, down, forward, back. Now, don't confuse that with the fact that if you look at this problem, this kind of overly simplifies how you might actually get a satellite to escape. Because this is really saying, in order to escape, you have to have enough energy to equal 0. That's really what this is saying. Fair enough? Now, that energy does not have to only come from the kinetic energy at the surface of the Earth to begin. like this problem implies. This problem is simply saying that once this thing starts, it has certain kinetic energy, and it can't get energy from any other source in order to escape. Whereas that's not quite how we build rockets. We actually put fuel on board, and they don't go very fast on the surface of the earth. And they go faster and faster and faster and faster and faster and faster and faster. And then they run out of fuel. But by the time they run out of fuel, depending on what you're trying to do to them, they may be significantly above the surface of the earth, and hence their escape speed at that point is much less than the 11,200. So if I had something already in orbit up here, then I would say I have to have an escape speed at that height. Now, it already has a speed in the fact that it was already at that orbit. So what I guess I'm trying to say here is it would be a difference problem. The thing to remember is you want the total energy to be 0 to escape. That's what you want. And if you have enough fuel on board, you don't have to ever go this speed. You can go 1 mile an hour for a long, long time and escape. Fair enough? You just have to have enough energy to escape. And so you have to have a lot of fuel on board. So this kind of overly simplifies it. I sometimes hear things like, for something to escape, it's got to go 11,200 meters per second. And that's not quite true. To escape and have no other energy source, it's got to go 11,200 meters per second. That's a better way of phrasing it. Yeah.
How does that speed compare to the speed of light?
Oh, not even close to the speed of light. Speed of light, which we usually symbol C, is 300 million meters per second. So 1, 2, 3, 4 decimals, 1/10,000th of the speed of light. So.
But it seemed like escaping Earth would have to approach infinity. Or what were you saying about approaching infinity? Yeah, to get to 0.
Well, to get to 0 potential energy, you've got to go all the way to infinity. So you never really get to infinity, obviously. So my point is you would never really have 0 potential energy. You would always have a little bit of negative, or a lot of negative, depending on how close you are to the planet. But that doesn't mean your total energy can't be positive. Because remember, your total energy is your potential, which is always going to come out to be a negative number, plus your kinetic, which is always going to be a positive. And if you put those two together, and you look at whether it's positive or negative, what I was trying to say, what would, if you put these together and it came out to be negative, tell you? Well, it would tell me that at some point it would have that much potential energy and therefore has no kinetic energy, and that's where it comes to a stop. So it can never get out to infinity. And so if you add up your energies, your positive kinetic and your negative potential, and you put them together and you come up with a negative number, that tells you you are never going to escape from the Earth. There's going to be some point where you will stop and come back.
If you're going at the escape velocity or faster than when it equal 0.
Right. Now, let's talk about the other thing. What if you added these two together and you got a positive number? Okay. If you add them together and get a positive, what does that mean? Well, that means that as you move further out, the lowest your potential energy could ever get is 0. And that's when you get infinite away. And when you get infinite away, That would be zero potential, but you would still then must have some more kinetic, so you would still be moving away. And that's what I meant by you are now free. You have escaped. And so the zero is the transition from when you would eventually stop and fall back versus never stop. Now, you may argue that zero is the place where you would keep going and you would get slower and slower, and you would never really get to an infinite distance away. But if you did get an infinite distance away, you would now stop. So that's why we call it the escape speed. This is the minimum amount you would have to never come back. Yeah.
I understand the escape equation. There's no M2. Does that mean
Right.
you could launch a skyscraper at that speed and it would escape?
Yeah. Yeah.
Negligible of any mass of an object
Yeah, but no, wait a minute.
within the atmosphere.
But you say that like it's a big surprise. Let's go back to chapter 8. I mean, in chapter 8, if I had the Earth and it was flat here, and I said, let's take an object of mass m, whether it be a baseball or a skyscraper, and you shoot it up, and you ask, how high does it go? H. You would have said, okay, I start off with a kinetic energy of 1/2 mv squared. Let me call the ground zero potential energy. And then it gets up to the top where it stops, it would be mgh. The m's would cancel off. And so you would say that the height that it goes would be v squared over 2g, right? Regardless of what mass it has. So you can launch a baseball or a skyscraper. Whatever speed you launch it at, that determines how high it goes. And that's not even different here. So I'm doing the same thing here. I'm just saying that how much speed it has is irrelevant to how much mass it has. Kind of makes sense because the force of gravity depends on how much mass it has. So if it had more mass, then of course there'd be more force of gravity. But it would also have more inertia, which would be harder to slow it down, and those two balance themselves. So you have the same acceleration. It's the same thing we did back in chapter 1. We took two objects, we dropped them, and we said they had the same acceleration. It didn't matter if it was a big skyscraper or a baseball. Same acceleration. So the same mass hopefully doesn't throw you off. Now, that being said, that doesn't mean they have the same amount of energy. Right. And so certainly the skyscraper at 3,000 meters per second has a lot more energy. So if you're going to get a skyscraper to go fast enough to escape, it's going to take a lot of energy compared to a baseball. Yeah, so there's a difference between a baseball and a skyscraper. But the difference is not in how fast they have to go. The difference is how much energy you have to give them to that speed of 11,200 meters per second before they escape. Okay? Now, by the way, notice that this equation for the escape speed looked a lot like an equation we had a little bit earlier. We had an equation that I put on the board, and it was actually derived last time. Remember that one? And I put it on here again today because this was the speed, and I'll just call it OB for the speed in the orbit, right? This is where we had used the universal law of gravity and the centripetal acceleration, and we put those together. So that would be the speed of something in orbit. But I think because the equations are so close, it's very easy for the beginning student to mix those together. So one has a factor of 2 in it under the square root, the other one does not. So you would say that this speed is not enough to escape. Yeah, that's why it's in an orbit. It's not going to escape. Yeah. If you took that same speed and pointed it straight out, it would go up and fall back down. It just would not escape. In fact, to finish up the chapter, maybe we should then talk about the energy in an orbit, because the escape energy, as we just argued, I think was the easier one to talk about. It was a total energy of 0. Basically, we said if you took 1/2 times the mass times the escape speed squared, and then you included that with the potential energy, that should equal 0. That's how we got the escape speed. We did a conservation of energy. We said if your total energy is so much, that it will never come back. Now, never come back means it's way over there, zero potential energy, and maybe barely moving, so zero kinetic energy. That's where I got the zero. That's why I said that working with negative potential energies now is actually kind of a blessing in disguise. It didn't look that way at first, but it's actually quite nice, and that's something I think you got to get used to. But that is the escape speed. Whereas if I was talking about a satellite that's in orbit, then I would say this is the energy a satellite needs to orbit, right? How much energy does it need to orbit? And so notice I'm not getting all the way away from the Earth, so I expect this to be a negative number. Now, I also expect it to be more than the value of the surface of the Earth. But if I go ahead and then put what we derived earlier for the speed of an orbit, then this becomes the g m1 over the r, and this becomes a minus g m12 over r. This would be the energy an orbiting satellite would need. And fortunately, they're like terms. That was kind of nice. And so this has a positive 1/2 and a negative 1, leaving me with a negative 1/2 g m1 m2 over r. And just to make it clear, this r, since it is not on the surface of the Earth, is not the radius of the Earth. This is the radius of Earth plus its altitude. All right, that's how high up it is as it goes around. See, because this, remember, is the velocity based upon the radius of the orbit, not the radius of the Earth. It's where the object is, and this also too. So I want to make it clear what R we're talking about. There's so many R's in here that's probably the biggest challenge of doing these problems is keeping straight what R's are we talking about. But notice then that is a negative number. And so what does that tell me? Yeah, even though the satellite is moving and has therefore a lot of kinetic energy, it is not enough kinetic energy to make the total energy equal 0. It will not escape. It will stay near the planet. It will, in this case, orbit the planet. Notice also that the equation we had for potential energy was a negative g m1 m2 over r. Which, again, if we're talking about a satellite that is above the Earth by a distance of h, notice then that this number, just the potential energy of it, is more negative than that one. And that makes sense, because isn't this one supposed to be the potential energy and then plus the kinetic energy, right? And so this is the kinetic energy. Notice a positive number. And so it doesn't surprise me that the total energy is bigger, and I should say less negative, than that one. This is its potential energy. When I add to it its kinetic energy, I get a bigger number. But that bigger number is still less than 0 because it is trapped by the Earth. And so the plus and minus signs, the 0, actually is a blessing in disguise, is what I'd like to say here. It's actually nice to talk about 0 energy this way. And it sounds funny, though, when you say, hey, if you want a satellite to escape, you've got to give it so much energy that it equals 0. And that, I think, sounds a little bit funny. But that's why I like to use it. It keeps emphasizing where I think students have run into some troubles in the past. Let me finish just with one more, and then perfect timing here to go on to the next chapter here. But I thought it might be fun to do a calculation that says, okay, what is the escape speed from Mars? And I'm hoping you'll see it would be the same type of calculation, right? If you were on the surface of Mars, you would, of course, say, okay, how much speed does something have to have? And then its potential energy. And of course, it would be the same mathematics. The difference being that the m would be for the planet Mars, and the radius would be for the planet Mars. And so, when and if we ever land on Mars, if those who land want to come back, which probably the first colony will not have an option of coming back. That's going to be what the New World is all about there. Kind of like the going to America. I mean, if you left Europe and went to America, it was a one-way trip. It was, all right, you can make it. You have no money. You'll be an indentured servant for 10 years, and you will never make enough money to come back. So, good luck. We wish you best. Say goodbye to your family. You will never see them again. And there might a 50-50 chance you'll ever survive. And Mars is going to be the same way. And in fact, Jamestown, right, was the colony that even to this day we can't figure out what happened to those people in Jamestown. They dropped them off, the ship left, back 10 years later or whatever it was, and where's the colony? Oh, where are the people? I don't know. Where's their bodies? I don't know. Where are they? I don't know. We've been digging ever since. Where'd they go? I don't know. And so what happened to those people? Sounds like we'll never find out. Hopefully that won't happen to the first people going to Mars, but it would not be a surprise if many of the trips did not make it. But just out of curiosity, to show you, you're not coming back. And we could compare this to the moon. You can land on the moon and come back. It's not that hard to get off the surface of the moon. The escape speed is pretty low. You could almost hit a golf ball fast enough to never come back. But leaving Mars, now it's not as much as Earth. So that's kind of the good thing and part of what I wanted you to see here. But if I put 2 times 6.67 times 10 to the negative 11, and then I multiply, mass of Mars. So what is Mars mass? 6.42 times 10 to the 23rd. So it's about 10 times lower in mass than the Earth. It looks like it has about half the radius too. So 3.37 times 10 to the 6th is the radius. And I take the square root of all of that, I get an escape speed of about 5,041 meters per second. And that is a lot less than the escape speed from Earth. So getting off Mars is not nearly as challenging as getting off of Earth. But it is still a significant challenge. And in fact, I just can't resist now. What is it for the moon? And so let's look at the moon here. 2 times 6.67 times 10 to the negative 11 times the mass of the moon, which is 7.36 times 10 to the 22, so about 100 times lighter than our Earth, and a radius of 1.74 times 10 to the 6th. Take the square root of all of that. Oh, that's higher than I thought. 2,400 meters per second in order to escape off the moon. But either way, like I said, particularly Mars, it's pretty much kind of in at least the current plans, that the first people to colonize it are probably going to land, and with the idea this is a one-way trip. You land, you try to make a life for yourself and you deal with the elements that are there, and you'll never have enough elements to build a rocket ship to get this much speed to come back, at least the first generation. It'll take some time after that. But the other reason I picked that up is Mars is an interesting one because it is one planet out from Earth, and it is small enough that these are the type of speeds you get when a meteor crashes in and particles blow out. I say that because if we have a giant meteorite that crashes into, say, the Earth, they usually go up and then stop and then come back down. But when they hit Mars, what happens? Impact, giant crater, pieces fly out, and they're greater than the escape velocity. So they don't come back, but then they get pulled in by gravity, the sun, and then the Earth swings by, and then what happens? Yeah, and then the Earth sucks them in, and then they come flying out of the sky. And so every summer or winter, depending on whose season you count it, the scientists are out going across the ice in Antarctica, because if you see a black rock on top of white ice, it's pretty easy to find. And when you have a black rock sitting on top of 9,000 feet of ice, where did it come from? Right, little aliens left them there. No, they fell from the sky. And so there's a good chance. And so we get a lot of our meteorites by scanning Antarctica and then looking around on top of the ice and seeing what came down. And so we've collected quite a surprising bit of Martian information. Not that we've ever traveled to Mars to see the rocks like we have done with the moon, but because of this interesting dynamics of the lower escape velocity, the fact that it's one planet out, and just everything just kind of falls in place for us. Yeah.
Isn't there like a company trying to colonize Mars by like 2022?
Yeah. That's what I was referring to. It's that same guy who SpaceX. What's his name?
Elon Musk. There's multiple.
Musk. Oh, there's multiple.
There's a reality show. They signed up a bunch of people to send to Mars by 2020 or 2025.
2025. Okay.
It's probably not going to happen.
Yeah. But that's it. Everybody's giving it a try. Things are coming along, making plans. They'll never work out like you originally envisioned, but eventually they will work out. And so, some of these things, and just as well, some of these things we find out more information. For example, obviously, where's the best place to land, so that at least you could get some ice, water ice, so that you could at least melt that, so you could have some water. Because I think that's obviously one of the things you want to look for first, is what are the chances of us landing there. And so we've got to get a hold of some water. And fortunately, we have confirmed that there is water there on Mars, and so and a lot more than we thought. So that solves one problem. You don't have to bring water with you or manufacture the water. That's big. Which then, through electrolysis, also gives you oxygen, I should point out. So that's the other nice thing. So you can get oxygen, another important ingredient you'll need to colonize Mars. So anyways, I didn't mean to quite digress into all that, but it's fun physics nonetheless. But we better move on. Let's go into chapter here 14. We've got about 55 minutes left here, and I would like you to see Archimedes Principle here in class before we try to perform an experiment in lab, because like I said, I'm going to try to do maybe a little too much in lab today, where we're going to run an experiment, albeit a short one, and also go over the test, albeit a little bit on the fast side. And so that's kind of what I'm trying to squeeze in here this last week. The last little part of chapter 14, the last lab, and also going over the test here. But there's really two main pieces of chapter 14 that I want you to get a hold of. And one is Archimedes' Principle, so that's the goal here for today. The other, by the way, is Bernoulli's Principle, but we'll worry about that on Wednesday. And so that's the second big piece. But chapter 14, as you will quickly see, is a little bit different than any of the other chapters we have done, because this is the first time that we've dealt with any fluids. And so this chapter is called Fluid Mechanics. And so, as you know, we've been dealing with mechanics, and I would say this is what the mechanics of solid. And this is the main part of this semester, is obviously the mechanics of solids. But this is a thrown out here to give you a little bit of information about fluids. For better or worse, dealing with fluids becomes mathematically complicated real quickly. So to do a lot with fluids, you have to really know differential equations, which at our school we call that Math 220. So it's a little beyond the scope of where we are. That's why we only have this one quick, short kind of hit once and then walk away from before it gets complicated, fluids. Okay? That's not to say you won't see this later. Most of you will end up taking what will be called fluid mechanics or fluid dynamics when you transfer, but again, not here, because just like before you could take this class, you had to take calculus. Before you could take fluid dynamics, you must take differential equations. And so you guys are building up to that. Some of you guys might already be in differential equations now, but most of you are probably in 160, and within a couple semesters you will be done with your differential equations. And so your last semester here, you will probably take differential equations, then you'll transfer, and then you'll be in a perfect place to take fluid dynamics. And so that'll be one of your first classes you take when you transfer to the university. But, like I said, there are some things we can do without differential equations. And so there are two main ideas. Basically, we could do fluids without any friction, without any, what viscosity is the fancy word when we come to fluids. And so all of our fluids will be just either not moving, static, or if they move, we'll say, well, they move without friction. So a little bit less than reality, but a good place to start. All right, so that's kind of the background of where we're headed with this. And we start off with mass density. I think you already know the concept of mass density. We dealt with it, well, way back in Physics 102, before you even started this class. I think we even used mass density as an example in Chapter 1, but we really ran into it when we needed the size of an object. So in Chapters 9 and 10 and 11, we talked about mass density. So let me just put the symbol rho, just to remind you then that it's mass per volume. I guess mathematically, we would write this as m over capital V, not little v for velocity, but capital V. And so there is one quantity I wanted to remind you of. Another quantity that's going to become very useful that we have not dealt with this semester, but I know you've dealt with it in your previous physics class, is called pressure. It's symbol with a capital P, which we also used power with a capital P, so don't confuse this. I'm not talking about power. Now we used a little p for momentum, but sometimes a little p and a capital P are hard to tell also. So this P is for pressure. This is not for momentum and not for power. Maybe I should ask you guys, anybody remember from 102 the definition of pressure? Yeah, and so it is how much force divided by how much area it is spread out. And so symbols would be something like this, F over A. Okay. What would the units be? Yeah, newtons per square meter. And this is named after the great scientists in the past, named after pascals. So we will measure pressure in pascals. Again, I suppose many of you are used to PSI. What does PSI stand for? pounds per square inch. So that would be an English measurement. So that's why we won't be using it here in our science class. But that is also why you will come across it many times, already in your lifetime and in your future, because the force would be measured in pounds and the area would be measured in square inches. So PSI is a common one here in the United States. In fact, maybe I'll just use PSI for a quick second, because I know this. I know that my car looking something like that sits on the ground. The tires kind of flatten out, hopefully not that much, but they sit there, they're kind of flat there. And I know that my car has a force or a weight of 3,500 pounds. So that's the force pulling my car down. So I must have that much force pushing my car up if it is to be just, staying there. Okay? And so how much pressure do I put in my car tires? Well, that comes to area. Now, first of all, I know I have 4 tires. So the total area that is pushing upward, the pressure, the molecules that are in those tires that are providing the lift that is keeping my car from falling, is obviously then 4 times the area of 1. And if I look closely, my tire is roughly about 5 inches by 5 inches. It's got a width of about 5 inches. When it looks flat, it's roughly about 5 inches that way. So the area is roughly 25 square inches. All right, so doing a quick calculation, I get 3,500 pounds. I get 4 times 25 square inches. That then comes out to be 35 pounds for every square inch. And so, sure enough, if I go to my passenger door and I open it up, and I bet you will too, there'll be a little stamp put there by the engineers who designed it, and it says, inflate your tires to, and there'll be a number. And in my case, it happens to be 35 PSI. And so I can put a pressure gauge on there. And if it is not 35, I can either add air or take air out to get it to the right value. Usually air comes out on its own, so I never worry about it being too high. I do worry about it being too low because the air leaks out. In fact, I can even tell when it leaks out. How could I tell when the tires are too low? What does it look like? Flatter, and the sidewalls bulge out. Why? So go on, what, is the car heavier now? No? Right, so in order to have the force to lift up my car, it would be pressure times area, right? And so if this number right there, pressure goes down, maybe I should draw it this way. So the pressure goes down, maybe from 35 to maybe 32. What's going to happen? The area has to go up. I have to have more contact with the road. And so more and more of that tire is then in contact with the road. And it's beginning to make the sidewalls bulge out. And after a little while, I begin to notice it. Go, that's, I guess I should fill it up before I notice it, but I never do. Hopefully you're better than me. I'm sure you check your tire pressures every time you fill up for gas. Like good citizens that you are here. Check the oil and all those things there. All right. But that is what I would call kind of our Physics 102, or our stuff that you've seen before, but it's good to remember, especially right here. Because then it was Archimedes who comes along and notices something interesting. And this is the lab you're going to do. you're going to do something along these lines. You're going to take a rock, and the first thing you're going to do is you're going to hold it in the air with a scale and take a reading. Now, if I were to ask you what's the weight of the rock, what would you say? $17? And this is in newtons. So let's go back to the metric system. So you would say the rock is 17 newtons? What if I were to push up on the rock a little bit? What does it weigh now? So did its weight really change? Or did the reading on the scale change? So let's be careful here. What did we mean by weight? Yeah, so here's a rock. And what we called weight was the force of gravity. Fair enough? And before this last chapter, we said it was mg. In this last chapter, we said if you're in the Earth's atmosphere, just use mg. So I'm in the Earth's atmosphere, so I'm going to go back to this mg that we got way back in chapter 5 and say that is the weight of the rock. In other words, the weight of the rock is the pull down by gravity. But what does the scale do? The scale is reading the pole upward. Let me call it F. And if I just hold that scale out there with the rock on there, and I do a free body diagram, then I get something that looks like this, weight pulling down and force of the scale pulling up. What do you know about the sum of all those forces? Equals 0, right? If the rock is not accelerating. And then the force up and the weight down have to give me 0. So doesn't that mean the reading on the scale is equal to the weight? At least that time. But what if I put my finger under it? How does this change? Free body diagram. So here's the rock again. The scale then is lifting up. Let's call it F. But then my hand is pushing up. What shall I call that one? Yeah, I don't want to use tension. Actually, tension would have been better for the scale. Oh, how about if I just call it normal? And normal force, because my hand's kind of like a surface. All right, so I'll just call it N. It's a different symbol. But isn't the rock still being pulled down by gravity? And so the sum of all the forces have to be 0 because it's just balancing up there. And so I've got force lifting it up. I've got my normal force from my hand lifting it up. Those two are up minus the weight. So what is the reading on the scale?
Weight minus normal force.
See why the scale reads less? So let me ask it again. Did the rock actually weigh less? No. Did the scale read less? Yes. I wish it really did weigh less, because I'd tell you what I would do. I'd go home right now. I would get on my bathroom scale, and as I stand on it, I would then lean on the counter, go, look, I weigh less. Isn't that great? But the truth is, that doesn't make you weigh less. This rock doesn't weigh less. The reading on the scale reads less, but that's not what weight is. Weight is the force of gravity. Another one that you hear a lot of times, you say, let's put on a parachute and jump out of an airplane. Are you weightless? You're not weightless. Are you falling to the earth? And why are you being pulled to the earth? Because of gravity. That is your weight. You wouldn't be being pulled down to the earth if you didn't have weight. Of course you have weight. And so when you say you are weightless, again, you're saying, what would a scale read? If you were falling and you put a scale underneath your feet, it would read 0. Yes, that's true. But that doesn't mean you weigh nothing. If you weighed nothing, there wouldn't be a force pulling you down. And so by me putting my hand under it is me kind of doing a silly example to say, do you really understand what do we mean by weight? And what do we get by the reading on the scale? Scales do not always read weight. They can be fudged. I mean, these right here were fudged, and this one was fudged by me putting another force. I could fudge it by pulling it upward, right? I could just say, here is the scale, and if I pull it upward, while it's going upward, it reads something totally different, because, again, the sum of the forces in that case doesn't have to be 0. In that case, the sum of the forces, force up minus weight, would have to equal to ma. And if it's accelerating upward, then the reading on the scale is not just the weight, it's weight plus the acceleration of the object. And so again, want to emphasize, don't confuse the reading on the scale with the weight of the object. The weight of the object is the force due to gravity. The reading on the scale is the force, that the scale is applying based upon, in this case, a string, and it can be tricked, if you will. And so reading on the scales is not necessarily the weight of the object. That's why if you ever go fishing, the best picture to take is always because when it's a snapshot, nobody sees your hand going up. But the reading on the scale is like, wow, look at the size of fish. God, it's huge, right? That's a 14-pound bass. Sweet. Good catch. But you can trick the scale. And it is you might call a false reading if your goal was to find your weight. And my goal here is not to get a false reading. My goal is, do you understand what I mean here by a scale? Here's why. And here's where the fluids come in. Here's where Archimedes Principle comes in. So hopefully I didn't damage it too much by pulling it so hard. So I would say right here, the scale reads 17. And I would say it also weighs 17. But when I put my hand on it, maybe I'll put it about 11. Doesn't the scale read 11? But what's the weight of the rock? It's still 17. So what does that say about my hand? My hand must be pushing up with 6. Fair enough? And so if you've ever seen this go underwater, does the rock weigh less? No. Does the reading on the scale read less? Yes. And why?
Water. Pushing it up.
The water, like my hand, has the ability to lift it up. We call this a buoyancy. And that's part of Archimedes' principle. Archimedes' principle is actually his discovery to say, how big is the buoyant force? And that's what we'll hopefully, we should have enough time, to discover before today's over. And that's what we're going to do the lab on. And this first step is just to show you there even is a buoyant force. I wanted you to see that if I put that on the scale underwater, it reads less. Not that the rock weighs less, but that the water is lifting up. And so just like my hand was underneath the rock lifting up, the water is underneath the rock and lifting it up. That is called a buoyant force. And so Archimedes' first part here is to realize that there is this thing called a buoyant force. And so maybe in a diagram here, I'll say, okay, here is an aquarium. Here then is a rock underneath. That rock would be pulled up by the force from the scale, but it's also going to be lifted up by a buoyant force. The water creates an upward force. And so in this case, the sum of all of those forces has to be 0. So we got the reading on the scale. We got and let's just call this B for buoyant force. we got the buoyant force, those two are lifting up, and we got weight pushing down. And so step 1 out of 3 steps is to illustrate there is a buoyant force. And I hope in this next half hour I will show you A, there is a buoyant force, B, what causes that buoyant force, and C, what is the value or predicted value of that buoyant force. Because what you're going to do in lab today is you are going to use Archimedes Principle to make a predicted value of the buoyant force. You are also going to measure the buoyant force and compare if what you measure and what you predicted is the same. Here is your measure. You are going to do exactly an experiment like this. Let me solve this for buoyant force. How would I get buoyant force? Weight minus F, right? So you'll see when we get into lab, I will say, here are your first 2 steps. Step 1, find the weight of the object. And so what you will do is you will take the object and you will weigh it, what I'll say, in the air. You will just take your scale, you will take the weight, you'll put it at the end, you'll take a reading right now. Because the reading on the scale is the weight when it's in a situation like this. Step 2, you are then going to dunk it underwater, and you're going to take a reading again. And that will be the reading on the scale when it is underwater. And now if you subtract the 2, and so I'll say in air and I'll say then underwater, but if you subtract the 2, you're going to get the buoyant force. And so that's going to be your first step, to find the buoyant force. And actually, you're going to end up doing it 6 times. Not the same thing 6 times, but I want you to see a couple of things here. Because what do you think would happen if I changed it from a rock to a piece of copper? Would there still be a buoyant force? Yeah. And so what you're supposed to notice, and you'll have a bunch of metals to pick from, you're asked to pick any 2. I always recommend pick the big one first, which is, we have the aluminum as our biggest one. So I'll say grab an aluminum one, and then as your second one, grab, and we have like zinc and tin and copper and lead and brass. Let's just say you grab aluminum and brass. So you're supposed to notice in the experiment today that if I put the aluminum in there, there is a buoyant force. And then you put the brass in there, and it too is a buoyant force. And hopefully the point being here is that the buoyant force is actually caused by the water. It's not by the material itself. Fair enough? Now, you may get a different number only because, as you'll see here, our piece of aluminum and our piece of brass aren't the same size. Same thing here. I didn't bother to get another string there. But I would get a different buoyant force just because they're different sizes. But everything that goes underwater has then different buoyant forces. That's my main point. Now, that being said, what if it wasn't water? What if it was another liquid? And so after you put it in water, you're asked to do the same thing by putting it under, we have some isopropyl alcohol. And so what happens if you put it in the alcohol? Will there be a buoyant force? Yeah. And so when you get a chance, hopefully you'll see that it's not something special about the water. Now, you get a different number. So there is something different between the water and the isopropyl alcohol. In fact, you do it a 3rd time. That's why I say you do it 6 times. Because we have 3 fluids and 2 different samples. And so you will put each of your 2 samples into each of the 3 liquids. The first one being water, the second one being isopropyl alcohol, and the third one being a salt water. We have a mixture of a lot of salt. It's not just salty like the ocean is salty. This is real salty. It's got a mixture of all the salts we could possibly put in there to make it basically as dense and different from water as we possibly could. Yeah.
Is it like saturated?
Is it what?
Saturated?
Yeah, definitely saturated. And then each of the different salts are saturated. So it's not just saturated with one salt, it's saturated with different salts. So it is, and we'll measure the density. You'll see it is really dense. It's about 20% denser than water. Whereas the ocean here is only about 5 to 6% more dense than water. So it does have salt in it, but nothing like we're going to do in the lab today. Yeah.
Is there a buoyant force like just from the air?
Yes, and there would be a buoyant force from the air. Right. Yes.
Right now, like where it's being buoyant force kind of.
Right, and so right now you are being lifted up by a buoyant force. So when you stand on that scale, I hate to tell you, you actually weigh a little more. Yeah, maybe for your guys' age that's a good thing, I don't know. But for my age it's not a good thing. I weigh more than that. But as you'll see when we do the calculation, the buoyant force from air is really, really small. But it's not from water, and I think you probably have noticed that. So like I said, the point being in today's lab is to get you familiar with this buoyant force. And this first step is just to convince you that there is a buoyant force. And that buoyant force does not come from the object itself. It actually comes from the fluid. And that's why we put the two different materials in there. But we also use different fluids to show you that each fluid is giving it a buoyant force, but it's a different amount of buoyant force. And so, like I said, hopefully we'll be ready to address that in lab here in just a second. But point number one, I think I got across. There is a buoyant force. Let's look at the cause. Why would there even be a buoyant force? Well, let me ask you this. You've probably experienced this both underwater and, as you pointed out, in the air. You ever dive into a swimming pool or the ocean and go deep? What do you notice right away? Pressure. The pressure. Your ears are really sensitive to the pressure changes. Same thing about driving in the mountains or flying in an airplane. If you go up or down the mountains or up and down an airplane, you can notice this right away. What happens? Yeah, your ears pop. There's obviously some kind of pressure changes going on here. And so if you don't already know, there is more pressure down here. So I'll put down here as high pressure. Whereas up here would be low pressure. Oh, let's do some numbers in a minute, but it's why I kind of brought this very simple experiment out here. This 2-liter bottle has holes drilled in it. And the water will come shooting out based on the pressure being pushed out. Which one's being pushed out the most? The one at the bottom. So in case you haven't been deep in a swimming pool or the ocean, hopefully this will convince you that there is more pressure the deeper you go. Let's see if we can get a little formula for that, because that formula is going to be useful into calculating the last step. What is the buoyant force? Okay. And so if I were to look at, say, a box of water. And so let me just take a box. Okay, now I'll say it's a box, but it's a box of water. So drawing on here, I'm looking at something like that. There's my box of water. Actually, I'm going to make a bigger box because eventually I want a box the size of this piece of wood. So if I kind of outline that, imagine then a box of water. Okay? Now, What about that box of water? Well, let me draw it over here. Here's my box of water. What would you say about the motion of this box of water? Nothing. Stationary. All right. So what did we learn about the sum of the forces? 0. So I would say that based on that information, whatever is pushing on this box must add up to be 0. All right. Well, what is pushing on this box? I mean, let's draw the free body diagram. Yeah, you might say, well, there's all these other boxes above it. Okay? So that is what's pushing down. I would say that is creating a pressure. Let me call that P1, right? There's a pressure on top. And if I take the pressure on top and multiply by the area, isn't that force number 1 pushing down on the box? All these other ones above it? What else is pushing on this box? Okay, this box is filled with water, so there would be gravity. Agreed? Okay, anything else? All right, good. And maybe the hardest one is underneath the box. Are the boxes underneath lifting up? Yeah, right? You stack a bunch of boxes, right? And when those boxes on top push down, don't the ones underneath have to push back up? All right. So I'll call that pressure number 2. Did you notice that I said pressure number 2 is not the same as pressure number 1? Right? So let me call this force number 2. So there's the free body diagram. Now, you might say, what about left and right and forward, back? Let me just throw those out and ignore those for a moment and just kind of wave my hands and say, yeah, those are going to cancel. But it's the up and down I want to focus on here, because it's the up and down that has to do with the pressure at the bottom and the top of the box here. See, because if I were adding these together, I would say, well, F1 is pushing down, gravity is pushing down, and F2 is pushing up. All right. Now, F1, as you just said, is pressure number 1 times the area. Weight is mg. Oh, forgot my minus sign. Number 2 is pressure number 2 times its area. If I were to rearrange this so that I put the positives on one side, I get pressure 2 times area. If I were to divide everything by area, I would get pressure number 2. Okay, so remember, number 2, that's the pressure underneath the box, would equal to what? Well, I guess I would say it is the pressure of number 1 plus mg over A. Well, let me pause right there. There's still some more math I want to do, but what is this really saying? Isn't it saying that the pressure below the box is the pressure on top of the box plus a little bit more? Right? Doesn't that match your experiment? Or my experiment up here and your experience with going under the water? Doesn't the pressure increase the deeper you go? And that's not quite obvious in this equation, but that's what this equation is trying to say. That the pressure at the bottom of the box is the pressure at the top plus a little bit more. The pressure increases with depth. Well, let's keep going. Let's put it in terms of the depth here. Because if I write this as pressure 2 equals, and so I'll write it as pressure 1, and let me do this little step here, mass. This is the mass of the water in that box, fair enough? can I write it then as density times the volume of the box? And the reason I put volume was because how would I get the volume of this box? Well, if this is the top, which we called the area, and I called the thickness of the box H, then this becomes area times H times G. And now remember, I'm dividing by A, so the A cancels off, and what do we end up with? Our first workable equation here, the pressure then is going to increase with depth. And here's how you would calculate it. The pressure increases based upon the density of the material you're in, which is water. Which you can see why in lab then we're going to give you different materials. We start with water, but then we do the salt water, as I said, which will be a lot denser, which is about 20% more dense. And then we switch over to the isopropyl alcohol, which is about 20% less dense than water. And so we have you try the different fluids to do Archimedes Principle, because again, the pressure does depend basically on weight. Yeah.
What's the unit for rho?
Oh, rho's density, I guess I've erased it, but density, which is mass per volume, so it would have units of kilograms per cubic meter. So if I do a little unit analysis here, I would have kilograms per cubic meter for the density of rho. Then I get meters per second squared for G. Then I get height in meters. If I put those together, that's a Newton. Canceling one of those, I get a Newton per square meter, which is a Pascal. So, as it should, I should have pressure in units of pascals. So it does work, yeah. Yeah, good question, unit analysis. Never forget it, yeah. It's always a good way to check to see if our logic is, working out okay. Because we know if our units didn't work out right, then something's got to be wrong with our logic. Unfortunately, just because our units work out right doesn't mean our logic is right. But at least it's a good check to see if we're doing anything wrong. All right, so as I said, there's three things I want to get across to you, and that is, number one, that there is a buoyant force. And I think I convinced you by just putting it on the scale. Number two, what is the cause of that buoyant force? And then number three, it's numerical calculation. But I think I'm getting the cause there. I don't know if you caught it, but looking at this box then, what would you say about force number 2 compared to force number 1? How does the force from all the boxes below compare to all the boxes above? Isn't it bigger? Isn't this saying that the pressure increases with depth? And so this is saying that you get a larger upward push from the water underneath than you get a downward push from the water above it. It is that difference that is the whole reason we even get a buoyant force. And so you observe that there is a buoyant force. I'm trying to say then the buoyant force then is caused from that. That part of the water is lifting up, part of the water is lifting down. The difference between those is the buoyant force. Okay? And so that is the cause of the buoyant force, what we call the pressure gradient. The fact that the pressure increases the deeper you go. Which, back to your air, would work for the air too, right? The air is higher in pressure the deeper we go, so we should get a buoyant force from the air. Well, the last part of this, and good, timing's working just about right here, is to say, all right, if there is a buoyant force, then what would be its numerical value. And this is Archimedes' principle. This is what Archimedes figured out. He figured out, as I said, there was a buoyant force. He figured out what was causing the buoyant force. And he gave us a numerical way to calculate that buoyant force. And I think you can see it here when you say it is pressure 2 times the area, and this is minus pressure 1 times the area. What did we say pressure 2 was? Well, it's pressure 1 plus rho GH times area. And if you subtract pressure 1 times A, then you can see that it's rho GH times area. And so this first term and that last term cancel off. Let's look a little closer at this equation. What's this right here? Yeah, isn't that the volume of that box? And so this would actually be density times volume times G. And let's take a closer look at that. What's this? Isn't that mass? Now, maybe I should emphasize mass of what? Now, it's the box of water. Now, the reason I say that then, as we are analyzing this, we said take a box of water. That box of water then is having a buoyant force equal to the weight of the box of water. Doesn't that make sense? I mean, the whole reason that box of water doesn't fall is because it is being pulled down by its weight, but it's being lifted up by its buoyant force. And its buoyant force is equal to its weight. That's why its net force comes out to be 0. That's why that little box of water doesn't go up and doesn't go down. And this then, and I want to be careful here, this then is the mass of the water. And the reason I keep saying that is, here's where it gets a little more complicated. What if in place of the water, I put a box of wood? Is there a buoyant force? And what does it equal? Isn't it still caused by the pressure at the bottom and the top? Notice then, and this is the experiment you're supposed to see today, that the buoyant force has nothing to do with the piece you put in there. The buoyant force comes from the fluid that's surrounding the piece. And it's equal to what? Now mg, but what m?
Water.
Is it the weight of the wood? No, it's the weight of what?
Water.
It's the weight of the water that would have been there. And so we call this then, oops, got my pen wet. The weight of the, and the fancy word is displaced water. The water that would have been there. And that's the brilliance of this analysis. Is it to convince you of those three things? Is there a buoyant force? Yes. What is the cause of this buoyant force? Well, the cause is the pressure gradient. That's why when you put something in there, you get a buoyant force. I don't care what you put in there, you will get a buoyant force. You can put a piece of wood, you can put some lead, a piece of iron, anything you want, you're going to get a buoyant force. It's caused by the fluid, not the object you put in there. And it is equal to what? It is equal to the weight of the fluid that has been displaced. Now up here I put the weight of the water since I'm working with water. But that is why you are asked in the lab to put in your object in water, then put it in alcohol, and then put it in salt water. Each of those have a different densities. Even though the same object is put in there, when you put this object into, say, alcohol, it displaces the same volume of alcohol. But is that the same weight? No. So will it have the same buoyant force? No. The buoyant force is equal to the weight of the displaced fluid. So why do some things float? For example, I put this in. I put this in, and it floats, right? If I let it go. So what would you say about this piece of wood?
It's less dense.
Okay, let me do that in 2 steps. I mean, the first thing I would say is since it got pushed to the top, doesn't that tell me the buoyant force is more than the weight of it? Right? And I know, let's say it again, what's the buoyant force? Equal to the weight of the water that has been displaced. In other words, if this thing was solid water, whatever it would weigh is the buoyant force. So this piece of wood must have less weight, or, as you said, less dense than water. And so you put anything under water that ends up floating. Oh, and I forgot them. Oh, wait. I left them on the back shelf. Anything that floats. Okay, I'm back. All right, I forgot all these. Foolish me. Okay, so we'll start with the simple ones here. But again, if I put that one in there, clearly it floats. No question about it. And that is just a way of saying that its buoyant force then must be greater than its weight, or put another way, since its weight is related to its volume and its density, something that has a lower density than the water would then float. So obviously this has a lower density and does float. If I were to pick something with a greater density, which clearly this copper does, actually it's brass. The brass does. I better not let it go because I think it'll break the bottom. But if I let it go, is there a buoyant force on it? Yeah, but it sinks. Why? Right, because it still weighs something, right? And in this case, its weight is more than its buoyant force. Could I calculate its buoyant force? As you will in the lab today. Yeah, how would I calculate its buoyant force? I would calculate how much something of that size and shape would weigh. Fair enough? And again, that's what you're going to do in the lab. So in the lab, as I said earlier, you're going to first experimentally measure the buoyant force. Then you're going to measure the dimensions of it together with the density of the fluid. Then you will calculate what the buoyant force should be, and you'll see those two should match for all 6 experiments. That's the idea. Some other things that float are pretty obvious. I got the styrofoam ball in here. If I put it underwater, is there a buoyant force on it? Yeah. And if I let it go, you can see it's a pretty big buoyant force compared to its weight, and so it pushes it up. If I take a can of Coke, does it have a buoyant force? Is it enough to make it float?
It's enough to stand.
It's just because probably a little air bubble in there, and so it's, one side's a little lighter than the other. So its center of mass is over here and kind of twists there. Okay, so does it float? No. What does that tell me? It weighs more than the buoyant force. Fair enough? It also tells me it's slightly more dense than water, which, by the way, do you know what the density of water is? 1 gram per cubic, or 1,000 liters per cubic meter, so it's a little bit more. Question?
So
I don't think so. I know what you're saying. The pressure's building up, but we're not losing any weight, right? The molecules are still trapped inside.
The density doesn't change.
No, unless the can gets bigger. And I guess it might a little bit, but I don't think it'll. Yeah. Don't want to lose my can of soda there. I'll shake it. But I can't imagine it. I mean, it's just going to turn them into a gas, but they're gas under a high pressure. There's still the same number of molecules in there, and the whole thing weighs the same. And the aluminum's pretty strong, so I don't think it's getting bigger. So I don't think any density has changed. How about the Diet Coke? If I put it in water, is there a buoyant force? But is it more than its weight? And it does. It has less sugar, right? And so its density is a little bit under 1, and so the Diet Coke ends up floating. I remember, it go back a long time, probably 30 years ago. But I remember on a water ski trip where we had our ice chest tip over. We were driving the water skis out to a little island, and we all fell over, horsing around too much. And the ice chest opens up, and we're like, oh. And we look around, and then there's some were floating. So we like grabbed all the ones that floated. So all we had all day was diet soda. I was like, ah. The only ones that floated were the diet. All the real stuff sank somewhere and down current, who knows where. There. But also, I think it is just kind of a human tendency to say wood floats. Does wood float because it's wood? No. It floats. Oops, I grabbed the wrong piece of wood. Bummer. I thought this was our high density. Yeah, maybe I won't go back and get it, but I'll show you on Wednesday that there is some woods. Now, most woods have a density less than 1, so most of us think of wood floating, but they all don't float. Same thing with rocks. Most rocks have a density greater than 1, so most of us think rocks sink. But not all rocks sink. It has nothing to do with whether it's made out of rock or wood. It is a matter of density. And I guess I'll finish with this last one, since that's all I brought out, and do more on Wednesday. But here's one that unfortunately with the optics it's kind of hard to see, but can you see there's a test tube in here? And I added some red tape on there because it was kind of hard to see a glass test tube in a clear water in a clear plastic bottle. But the test tube is upside down. You can see the red on it, and there's a little air bubble. Can you see the air bubble inside? And the air bubble's put in there because I have now a test tube that's probably about half filled with water and half filled with air. And it floats, doesn't it? So the density is less than water. It floats. Could I increase the density? I could if I put more water in there, less air. And I can do that by just kind of pressurizing it. Can you see the bubble get a little smaller? We'll do it again. Put a little air in there. Bubbles is a little smaller. Still floats. And now it sinks. Release the pressure. And now it floats. And so, squeeze it. More dense. I'll squeeze it. Less dense. Right about there is a good transition. So squeeze it, gets more dense, it sinks. Less dense. Actually, it probably stays down there because remember the pressure increases with depth. And so it's not, it's right there at that transition. But wells do this really well. This was a big confusing point for scientists for years. How in the world could a sperm well dive 5 miles deep, swim for a half hour hunting giant squid, swim 5 miles back up, or maybe it's more like 5,000 feet, so 1 mile down, 1 mile up. How could that have so much oxygen? And after putting a video camera on a whale, they discovered the whale doesn't swim. The whale can change its density. And it has wax, right? That's why they were hunted, for the wax, so that they can burn candles, and they were hunted almost to extinction. But that wax can either be a liquid or a solid. And so in the solid state, it's less dense. In the liquid state, it's more dense. And so we don't think about it, but if you had like a big ball of wax on your back, if you kind of brought it in to the internal parts, it would melt. You would become more dense and you would just sink. You don't have to swim. You just sink 5,000 feet. Then you swim and use your oxygen. Then you move the wax to the outside of your body. The liquid wax hardens. As it hardens, it becomes a little bigger and takes up more volume. You become less dense, and what happens to you? And you float back up to the top for 5,000 feet. So there's no swimming down or swimming back up. And then there's plenty of oxygen for the 30 minutes you can swim around and hunt for. All right, well, more on this on Wednesday. We'll do the lab this afternoon.